All right, let's begin. Now, let's begin by summarizing what we did last lecture. We did finish going through Griffith's energy balance, right? So the essential ideas are all there. He had the notion of surface energy, and he completed a thermodynamic energy analysis, and from there we derived, from the work of Griffith, an expression for the critical stress. Okay, so this is where we got to last lecture, right? And so we finished the analysis performed by Griffith, and it has a lot more a closer agreement with theoretical strength. And we remember he did two experiments which were very insightful, right? So he proved that the relation between stress and crack length is to the to 1 over square root of the crack length, right? So that is this dependence of stress on 1 over square root of the crack length, right? That is confirmed experimentally, and he also confirmed that for glass the constant equal to elastic modulus times the surface energy. Now, that is all good, but there is two aspects that are not very convenient from the Griffith analysis. First of all, it's all done on glass. So and for glass, it's a very brittle material, and you can use surface energy in the analysis. Now, that is okay. But if we want to apply that analysis to a different material like steel or other ductile solids, we immediately found out there's a discrepancy. And that is the work that we began talking about towards the end of last lecture. There's Irwin and Orwin. There's when they were dealing with the Navy ships, which were made out of steel. Now, so that's the first issue, that the surface energy is not accounting all the energy that is associated with breaking a piece of ductile solid into two pieces, right? So you advance a crack. In addition to surface energy, there's also a large amount of plastic deformation at the crack tip, and there's some energy dissipated because of that plastic deformation process. Okay, so that's the first. So to speak, a difficulty in applying to other materials, and indeed we talked about that also, very quickly. That it was actually very, it was solved or circumvented by Irwin and Orwin. Well, because we know this is plastic deformation. And that means that there's more resistance in addition to surface energy, and so then what we need to do is just to modify that surface energy term, right? Because that represents in the Griffith formula, that represents the only parameter that resists fracture from the material. Okay, there's only parameter that resisting fracture here, right? Stress is being applied, crack is just a geometric dimension of the crack, right? So what is really resisting is only the surface energy. So by the same nature, the plastic deformation energy is also a material property that is resisting the amount of energy for crack advancement, right? So that's where we stopped last time. Okay, and so the other aspect that is not very convenient in Griffith is that it's always in the form of a sigma, so which is a critical stress, and stress is not a good concept for describing fracture because it's not a material property. Okay, now there's the crack length that is explicitly there. So whenever we want to predict something or apply that formula to something else, or a piece of material that has a different crack length, then we always have to carry with us this A. Now, this is not convenient because we like to for example, compare two material just in terms of the intrinsic resistance to fracture, right? So we want to get rid of that crack length dependence, because, for example, if we want to compare glass and steel, having the same crack length, which one would give us a better fracture resistance, right? This is a material to material comparison, right? And we want to know that because in general, then we can rank materials, and we know that what sort of materials are good for resisting fracture. So we want to, so in the end of the day, we want a material property, right? So that is just intrinsic to the material, and that does not depend on other extrinsic factors like the crack length. And that is where most of what we're going to talk about today is going to reformulate Griffith's energy balance idea, but in terms of new terminologies, the analysis is entirely the same, but just we are changing, introducing new concepts, and modifying the analysis slightly. But actually, the end result is a lot more clear than what Griffith did, and most of the lecture today is due to the work of Irwin and Orwin. Now, the first thing that he defined. Well, instead of stress, we don't want to use stress because stress is, the critical stress is not material property. So what is the intrinsic in the material that does not depend on other things that resist fracture? Well, we just talked about it, right? It's the surface energy for glass. That is the surface energy that's intrinsic property, right? Doesn't matter what crack size it has, but it is the surface energy of the material. But for ductile material, it's going to be the plastic deformation energy, the WP, and the surface energy, the sum of both. Now, again, the WP is associated with the plastic deformation at the crack tip, right? So if you know a little bit about plasticity, when steel yields and deforms plastically, you have dislocations of the crystal planes. That is a microstructural processes that happen when you have permanent deformation, right? There's dislocation, slip planes, that sort of thing. Now, all that deformation, that change in the microstructure takes energy, requires energy input. So that is what this WP is physically, right? The energy goes into dislocating the planes, slipping the planes along each other before you can break them, right? So elastic material, linear elastic material, you don't have that mechanism because there's no dislocation before fracturing. Just not, it's just not how brittle material behaves. They don't have plasticity. They don't have this dislocation. And so now this is good, but again, this is still only ductile material, right? Can we generalize the concept to even more general setting, and that's where they come up with what we call the fracture energy. Okay, so I'm using this. So it's not a very commonly used term. I like to use it because it distinguishes what we're going to talk about very soon, which is critical energy, energy release rate. Now I like to call that fracture energy, right? And I put this large gamma here as my fracture energy, right? So what does that mean? So fracture energy, we'll define it as this is the amount of energy per unit area needed. Sorry, the energy required to advance a crack by a unit area. Okay, so you start with some pre-existing crack, something like here. This is the picture we drew last time as well. Just compare this and this. So we have a crack here. This is already plastic deformed, so there's a yielding zone here. So what is the amount of energy needed to make this crack increase by a length of a unit, length, right? And then you multiply by the width, that's unit area. So your crack advance, and there needs some energy to do it. The material resisted by some, the energy provided by the material to resist that crack advancement is the fracture energy. Now, so in other words, what we are saying is basically nothing new, right? So we take that fracture energy, and for ductile material, it's going to be 2 gamma, plus WP, right? Because we just say that for glass, brittle material, it's just going to be the surface energy. Now for ductile, it's more than that. Now, so we can slightly change our formula from Griffith to this form now, right? Just replacing all of that surface energy or plastic deformation, all encompassing in one term, which is the fracture energy, right? So now, what is the significance of doing that? Is that surface energy, because when we're dealing with a new material, we don't know what is the associated fracture mechanisms that is providing the energy resistance to fracture. Now, to writing that fracture energy explicitly in the equation then allows us to, we don't really need to know exactly whether it's surface energy or plastic deformation. I just need to know the sum of it. Whatever that contributions are, that's a deeper question, but I can deal with, or we can live with. We're just measuring the amount of energy. I can measure that, right? By experiments. I'll show you later on how do we measure that. And I don't care where it comes from, right? As long as I know that fracture energy is this much, it's good for me, because this is the resistance of the material that resists crack. I do the same experiment on a different material. I measure that fracture energy. I compare this to a fracture energy. I know this steel is more resistant to fracture than glass, right? So fracture energy is going to be higher in ductile steel than glass, right? So this is fracture energy. So just remember that, because we're going to formulate, the fracture energy criteria for fracture based on energy, right? So this is, think about it as, you have a crack, you have a body, that there's something you're doing to it, right? So you put forces onto it, that is the amount of work that you're putting into the material. And then the material itself has some intrinsic resistance, right? So there's fracture energy, right? So it's always the competition of these two, right? Whatever you put in, is it larger than what it can resist, right? So it's quite simple idea, right? It is the same as classical string theory you learn in solid mechanics. Is you put that amount of stress, and it has some critical failure stress in the material, and then if the applied stress is larger, then you break it. If not, then you don't break it, right? So same here, but now everything changes to energy. It's not stress. Everything changes to energy, but the idea is the same. We apply some energy, and there's also a fracture energy in the material. Now, but then the energy is, even though it says fracture energy is energy to advance a crack by the unit area. So there's a subtle difference. So the fracture energy has a unit, again, just like surface energy, right? So it's going to be joule, right, that's the unit for the fracture energy. Again, the same as the energy needed to advance the crack by some unit area, right? So that's the fracture energy. Now, so fracture energy is a material property. It is not dependent on the crack length, and we can measure that from experiment. So this is something we can get it. And typically it's much larger than surface energy, right? So because you have more than just surface energy at the crack tip, happening at the crack tip. Now, that's good. That's we have defined, an energy that based on the material resistance to fracture. Now we need to define, the corresponding, energy term that we apply to the material, right? So, and that is the concept that we call the energy release rate. And I'm going to just write that down and explain these terms one by one. Right? So this is the definition of it. G is the energy release rate. Is defined as the minus of the derivative of pi with respect to A. Now what is pi? Now pi here is the sum of elastic potential energy in the whatever you're testing, in the solid, whatever you're testing. And let's simplify this for just linear elastic material so it's easy for us to talk about it. Really, if this is just a linear elastic material, it's the sum of the elastic strain energy in the material plus the external work done. Okay? So elastic strain energy plus external work done. Okay? So very similar to what we did with Griffith's energy balance, right? In the Griffith energy balance, we still look at these things. How much elastic energy is being stored, what is the force applied, that's the work done, and elastic energy. But in Griffith, he also put in the surface energy in the same analysis, and then come to the critical stress. Now we want to separate these two things, basically, right? So we want to separate the elastic strain energy and external work done, because that is what you're doing to the material, okay? And then you have the surface energy or fractional energy that is independent of what you do to it. It just belongs to the material. So we are separating these two, basically. Now so therefore our energy term here are all energies that are actually due to the action of loading. And A here is the crack area, because we are talking about, analogous to the fracture energy, which is energy needed to advance the crack by unit area. We have the same, dimensions in this energy release rate concept, because that is the amount of, the sum of the elastic energy and the work done energy you're putting into the solid as the crack advances. Okay. So this is what it is, right? Now, or in other words, that is, what is the energy available to advance a crack by unit area? Right, so this is, right, fracture is the amount of energy to resist. This is the amount of energy that is available in the system to make it crack. So what we need to do is then to define the elastic energy pi, right? So pi. Oops. So elastic, the sum of the elastic energy and the external work done. Now, internal energy is U. That's the internal string energy. Now, work done to the system has the convention of minus F, right? So if this is the work done, F is the work done. We use minus because that's the work done. That's the external force, energy from the external force. So this is convention in thermodynamics, right? The energy being put into the system, it has a minus, right? Flowing into the system has minus. The system has an energy of U that's positive because it has that energy already. So this is just from a dynamics convention. Now let's just repeat very quickly. Using the new concepts of energy release rate and surface energy, just repeat Griffith's analysis, right? So and we'll see what is they're basically the same thing, right? So think about, let's rotate it. Now we have the Griffith experiment or the Griffith crack problem. And we said that we apply some stress, and at some point, and we fixed it so that it doesn't increase anymore. Some force. So this is the crack length A. We have, let's make it some thickness. Thickness B. So what is the energy release rate to this for this loading scenario that Griffith did. So he did by applying that amount of stress, and then he fixed the displacement. Okay. So the sum, if you remember, the external work done is going to be 0, right? From here to different with. So if you don't remember, you can go back to. I think it is the last lecture, I think, or the lecture before, right? The external work done difference is going to be 0 in Griffith experiment. So, and the difference in the internal energy is just this. So you have seen all this before, right? It's exactly the elastic energy difference. And in this case, our area is the thickness and times the crack length A, right? So for this, it's very simple, right? So we're going to do a bit more real example later on, but just to show you very quickly, how do we calculate? Oh, sorry, this is d pi dA, and in that case it's just the same as now, since our difference in the work done is F and we don't have F, so there's only U, and that is so U here, and we don't have F, right? So let's keep going. That means that we're looking at du dA. Now we just have to change A now to BA. Since B is a constant thickness, we can take it out of the equation. Minus 1 over B. D small a, right? Because there's a small a because of the crack length. And we have U. And U is just right over here. And so at the end of the day, we have G to be pi sigma square A E. Oops, sorry. This is for Griffith experiment, right? Now it's nothing new, right? So you see that the equation, if you just change sigma over on the outside, I mean, we introduce a new term which is called G. So what is the energy criterion then in terms of G? Well, I know that this is the energy available. If I have an experiment like this, I apply some stress onto a plate with a crack of 2A. What is the energy? The energy available to advance the crack is exactly this much, right? So it only depends on the elastic property and the crack length of the solid. Now, then what you want to do is that the criterion that we can write down is G larger than the fracture energy of the material, right? Basically, that is Griffith energy criterion, right? So it's not in terms of stress, it's now in terms of energy release rate and the fracture energy. Now, one comes from the material, one comes from whatever you are doing to the solid, right? So it's now independent of critical stress and all that, right? So this is something that we can use more conveniently. Now the fracture energy gamma, it's not a commonly used term. Fracture energy, you may see more that in textbooks and other literature is the critical energy release rate. Okay, critical energy release rate. I don't like to use that because it's awfully similar to energy release rate. It has named critical energy release rate. That means that if your the energy release rate applied to the material reaches the critical value of the material. Okay, so sometimes we call it the critical energy release rate. So I'm going to keep using fracture energy. That's how I like. I'm used to doing that. All right. So this is a simple problem. Let's look at a little bit more realistic, a more general case, right? In this experiment that Griffith did, he fixed displacement, and he make many different copies. Right, if you remember, crack that is slightly larger, and then applied the same displacement onto the material, right? So this is, for example, 2a plus delta a, right? And then he keep doing that, right? So that's why the work done is 0, right, from here to here, because the displacement is the same. Okay, so there's no work done. That's why it's 0 here, right? We explained that 2 lectures ago. The force are different, right? The force needed to go from here to delta is different from here, because this is slightly less stiff. The crack is slightly longer. So we go, but then if you compare these two, there's no difference, because the force does not move. There's no increase in work done, even though there's an increase in the force is different. That force is not creating, it's not moving, because we fix the displacement. There's no work done, right? Now, in general, we don't always have this situation where we can control the displacement, right? Sometimes we can control the force. We don't have control over the displacement. So in general, we do have both displacement and forces, which then gives us some work done. In that case, how do we calculate the energy release rate? So now we consider 2 cases, right? Basically there are 2 different cases. First one is low control, right? And the second is displacement control. So let's first talk about low control fracture experiment, right? So what we want to do is, now we have this concept of energy release rate. How do I calculate energy release rate? In general, in general situations where I have solids and they are loaded, not just by, fixing the displacement, right? I can just keeping a weight on it, right? The force is constant, the same force. The displacement is not. How do we calculate energy release rate in that case? So let's consider the first case where we have low control. Okay, so again, similar idea, right? So let's think about some crack, a crack, very sharp. I have a piece of solid just like Griffith, again with B initial crack length, small a. And I'm going to hang a weight, and that's called P. The weight force is P. It's just hanging down. And I will consider another very similar copy of the same configuration. With a slightly larger crack length, A plus dA, okay? And I got P here. Now, before you have the force P loaded, you have some original configuration, and then you hang a weight onto it. There's going to be some displacement, right? And I'm calling that delta, right? So it has moved by some amount. And that's delta. Now I got the same P here. And again, from unloaded to the equilibrium state, there's going to be some displacement of that solid. And this is going to be slightly more than delta, right? Because the crack length is a bit larger. So it's a little bit more compliant. So that's going to be delta plus d delta. Okay? Now that's good. So we want to draw then, we have defined the energy release rate. What we need to do is just to account for all these different energies. So what I'm going to do is, I can show you in a very quick way to do this, right? So we always want to think about this. What is the energy difference, right? That's very important because we are comparing configurations. So what is the energy needed to go from here over there, right? So that is it. So now think about, let's write down energy release rate definition. So we keep our mind clear on what we are looking after. Okay, just writing the same thing all down. Okay, now let's think about this configuration where we have, and just draw what is the low displacement curve for this guy. We have P here. We have the delta, or displacement. Let's say displacement. Yeah, call this load. P refers to a different thing. Right? At the equilibrium configuration, we got delta, and there's our P. Right? So this is just, a simple low displacement curve for this guy, right? This is linear elastic material, we assume, so it's always like a straight line here. Now this is for the configuration where the crack length is A, yes? And now think about the other configuration. So the weight is still P, okay? Now it has displaced a bit more, is D plus delta, D delta. So it's a bit larger. Delta plus D delta, this is a bit larger. And P is always the same because it's a dead weight, so it can't go above P. And it must be, equilibrium point must be right here, right? Because it's displacement here, P is, that's the only applied force. Then this is the low displacement response. Now the slope is slower as we expect. That means a slower slope. That means this is a bit more compliant. Now think about the energy of the two positions, right? So first of all, we have the energy of this guy, right? Just think about the energy of this guy. From 0 to some delta, there's some work done already, right? So I'm talking about the work done on this guy only. It's not a work done difference, all right? So we have to be very clear because it's very confusing sometimes. Now, I get, so for this configuration, let's call this A, and let's call this B, just to distinguish. Okay, so A and B, A is the one with smaller crack, B is the one with the larger crack. Now for A, what is the work done from 0 to the force being applied? That's going to be P delta, simply, yes. And what is the elastic energy being stored in that material? Well, we just have to integrate from 0 to delta d delta, right? So this represents the internal string energy, basically, right? Area under the curve, linear elastic material, and this gives you dP delta over 2, right? So again, this is all linear elastic, results that is well known. So we do the same thing, okay? Now we do the same thing for B, configuration B. Now the work done is what? From 0, from original configuration, and then I hang away P onto it. So the work, some work is being done because they're forced travel by some displacement, and that is exactly P delta plus D delta. Yes. So if you look at on this plot, right, this rectangle is the work done for A, and the larger rectangle is the work done for B. Just P. I'll just leave it here. Now, internal elastic strain energy. Now I have to integrate from 0 to delta plus d delta, because that is the final displacement. Again, the P is constant. Sorry, the P is not constant for the energy. Sorry, no. That P is the force inside the material, all right? It's not the loading force. Now, again, very simply, you get to this result. And again, if you look at this plot, you see that the area under that triangle is the elastic energy of this guy. Yes? Right? So U minus F, now we need to go to this, right? What is the pi for both? Again, configuration A, what is pi? Pi is U minus F for A. Is simply, let's do this. Oh, okay, perfect. I'm taking P delta 2 minus P delta, that is minus P delta over 2. And for B, now, yeah, so same here. I have U is delta plus d delta over 2 minus F. F for configuration B, the one with the larger crack, is P delta plus d delta. Again, the same, right? So P simply just this. So one way to visualize what is happening, right, graphically, is to look at this plot. This is, so if we look at the configuration A, this is the work done, right? That rectangle is the work done. The triangle is the elastic energy. So the difference of these two is the complementary energy, if you remember in solid mechanics, which is that triangle, the other triangle. Okay? Similarly, for configuration B, which we should be looking at, P, the larger rectangle, that is the work done for configuration B. Area under the curve is the strain energy of the configuration B. Now, the difference of these two is the complementary energy again of configuration B, which is this triangle, right? So you can see that there is two triangles, and the triangles mean what? That is pi. That is pi. You see? And there is a difference in pi between the two configurations. Just, as illustrated by the size of these two triangles, they're not the same. The pi is going to be slightly larger in the configuration B. Now, so we just need to capture all this, understanding in our equation, because that is really what is happening, right? Because we want to understand how the change in pi with respect to the crack area. Now we set this up to do exactly this, because I have two configurations with different crack length, and I account now what is the difference in pi. What I need to do is that I need to count in a way that I can formulate an equation such that it's a derivative that I increase the area a little bit. I have I can know how the energy change exactly analytically. Now, so let's put all these things together. What we need is the change in delta, because we are doing two configurations. Now I'm calling it d pi. D pi is just the difference between the two pi's in two different configurations. So I'm going to take B, because B is the one with the larger crack length, and I do that by the change of these is just, sorry, this is d delta. So if you just do that, you just go to get a result that is, again, fairly simple. It's going to be minus P d delta over 2. Okay, now I just need to assemble, right? dA is just dA, right? dA is just the crack length, and the crack length is just the width of the crack times dA, right? Because this is the change in the area. The area goes from this to this. There's just difference. Right? Let's put them together. G is minus d pi dA. That means that I just need to put them together. So P to B d delta dA. So this is the result for load control. Okay, so that means that if you have a P that is constant, the load is being fixed at the constant value. If you have a problem that is load control, you can find the energy release rate like this. Experimentally, this is exactly what you can do, because you can measure d delta, right? In the end of the day, we want to measure it, right? So you have a piece of glass. Oh, okay, I make 5 copies of this. I hang weights, same weight. I measure delta, and I measure the crack length correspondingly, right? What is the dA right? Because I know what dA is. I make the crack different lengths. I already know what dA is. And I have to measure the delta. So, and P is what is being applied, B is just geometry, so I can calculate the G for all of these different crack lengths. And what is the one that is most interesting? It's the one that, finally I make a crack that is so large. Once I hang the P in the low P there, it cracks, right? That is the critical energy release rate. And so I get that, and that critical energy release rate is the fracture energy of the material. And so I can note down on my notebook, well, you apply this much force, this crack length, I calculate the energy release rate, or this is the energy needed to crack the material. Now you can transfer that fracture energy to different structure and in provided analysis. So this is low control. Let me go through the displacement control more quickly. Right, the thought is the same. Right, so I'm not going to go through this in the same amount of detail. So this is displacement control, and also a very well used experiment, or in reality, right? So you see, we have elasticity boundary value problem is either traction boundary conditions or displacement boundary conditions, right? So it's either low control and displacement control in mechanical problems, and so you can always distinguish either of these. Now, in displacement control, what we mean is that we again load a material with some crack, pre-existing crack. Now the delta for these two is the same, okay? So I hang a weight on this one. Actually, okay, no. Hanging a weight is not a good way. So I grip the end of these two ends. I move until some delta is achieved, and then I fix it there, right? So this is, the original. Perhaps is here, right? Let's say the original is here, and I stretch it, and then I fix it at some displacement delta, and I do the same here. Right? So both of them have the same delta, right? That is the difference. Now again, the P is different now this time because this is less. This is a more compliant material, so the force needed to reach delta for this guy is less, right? Obviously, so the force is different, right? You specify the displacement, then the force is going to be different. Now the corresponding load displacement curve is this, okay? Original delta this is for the case where the crack is A. Now there's a configuration with a larger crack, pre-crack. It's going to be like this. It's going to be more compliant, so a smaller slope, and it has to stop at delta because I force it to stop at delta, and therefore it's not at the same value of P, right? At this configuration, this delta, this has a value of P, this one is less than P. I'll stop it there, right? So the plot looks like this. Now you look at again the complementary energy, the pi, there's going to be a difference again, right? The pi, again, it's this triangle over there, right? Now for this guy, Now it's different because now you have, this is string energy. Now the work done is right here. Okay? So the complementary energy is this guy, right? So now you need to figure out what is pi in difference in pi. Again, you're not going to do this over and over in reality. This is just to show you how, graphically it looks like. Again, we use the formula that thinking about the difference in the energy between these two configurations. All right, the change in. Let me show you a different way. Right, get to the same point. Change in work done between these two is 0. Okay, there's no change in work done. Right, because the crack moves a little bit more. There's no change in delta. Right. There's some change in the elastic strain energy, and that is, you can verify this because I'm not going to go through again, but you can go through the same process I went through with you previously. You get this same result. It's going to be P delta, and therefore our d pi is thinking about df, right? It's going to be P delta over 2. Okay, let me continue below. Well, dA again, not to make changes, is kind of BA. Oh, sorry, BDA. Oh, sorry, I'm missing a D here. Okay. So this is dP, right? The change in force, which is exactly here. P dP. All right, just the difference between the end load, right? This is P to reach delta. This is smaller, right? It's here, right? Exactly, it's just P plus delta P. So that you subtract the two, it becomes dP. So reassembling everything, G minus. Then you will get to the final result, which is minus delta 2b dP dA. Yep, should be, yeah. All right. So that is the other result is for displacement control. Yeah. Okay. Sorry. All right. So we are very close to the end. So you see we have two different formulas for displacement control and load control. We just summarize low controlled or low fixed. We got G to B. Displacement control G is right, that means fixed P or this is fixed delta. Now we can summarize these two equations in one equation by introducing one more concept, one more variable, which is the compliance. So the compliance, we call it C, is just delta P, right? So this is the compliance of the material, of the solid. You can measure that, very easily, because that is just the reciprocal of the elastic modulus, if you think about it, right? So the elastic modulus is, stress over strain, or load over displacement. This is displacement over load, right? So compliance is just reciprocal of stiffness. Compliance and stiffness, you multiply the two, you get 1, right? So compliance C is delta P. Now we can summarize these two equations into one by introducing that compliance into the equation, because let's look at the low displacement case, right? Low control case, and think about what is the derivative of dCdA. I can turn dCdA. I just take this over here, dA delta P. Now because that in low control my P is fixed, so it's not changing with crack length. So P is always the same, so it can be taken out. So it's going to be 1 P d delta dA, and that means if I change around, d delta dA is going to be P dCdA, right? Just very simple. Now this one can be substituted into this original formula, and you get G equal P squared 2B dCdA. Okay, just substitute that into here. So this is a different way of writing the energy release rate in the case of low control. Now, you're going to find this remarkable because it has a very simple form. In the displacement control, let's do the dCdA again. We have to be careful now because what is not changing is delta. Right, delta is being fixed, and we have dA 1 over P. And just use chain rule. Use chain rule in differentiation. You got P squared dPdA. And that means dPdA minus P squared delta. So you can go through it at home if you can't follow all of this right now. Now what you want to do is you substitute this one over here. Okay, so you substitute this over here, and then you, in the end, you will also get the same result. And if you compare this one and what we just derived, for low control, it's exactly the same. So we can actually describe all situations, both lower control and displacement control, by this energy release rate formula. Right, this is more easy to use than minus d pi dA, right? Because in that case you always need to go to count the energy. this one just require you to find out what is the compliance of the solid is, and then you can calculate the energy release rate. Okay, so good. Let's do an example just to see how we use this. How to calculate the energy release rate? Now we've been always dealing with a crack in a plate. Now can we do some other problems, because we don't always have a crack in a plate, right? Let's do a problem that is simple enough that we know how to calculate everything, and also quite practically useful. This is the configuration that is very well known as the double cantilever beam. Yeah. So the double cantilever beam is a configuration where we use all the time to measure the fracture the fracture energy of material, and it also represents a lot of practical situations where when materials are being fractured out, right? So let's do this. So it's called double cantilever beam. So think about this, right? You have this is very common in many things. So right? You have a piece of material that you kind of ply it out, right? So this is double cantilever beam configuration of fracture. You have two plates that are glued together. Now you want to peel it off, right? That's a crack problem, right? So what is? I mean, you typically use it in a reverse manner, because you want to glue strong enough that it does not, allow you to fracture that two piece of, slabs of whatever material you had, right? So this is a double cantilever beam configuration, right? The stress situation is exactly the same. So let me put on the. So you can look at this. This is the crack, right? There's a pre-crack in your solid already. Now, is it going to crack further, under the existing load? So think about this. This is like a cantilever beam problem, and so we actually know how to solve it, because we know beam theory, and we know how to solve the stress field, displacement, the displacement of the whole beam. Okay, so let me also put in this dimension. So this is the crack length A, the pre-crack, right? So from the mouth to the tip, this is A. And I'm going to define this. This is going to be delta, okay? And so this is symmetric. So this guy is just delta over 2. So in double cantilever beam, we do make an assumption that right over here, we assume that the beam is essentially cantilevered, okay, right here, right? So there's no deformation here, and then this beam is being bent by the load, and we want to see what is the energy release rate in this problem. And we want to calculate, and if we know the fracture energy, we will know then whether the double cantilever beam can resist a crack. So we want to use the formula we just derived. So I'm just going to write it down. So instead of using the original definition of minus d prime dA, I'm going to use the compliance formula. So I'm just writing it down, what we just wrote down. So remember, what is compliance C? C is delta over P. Yes? That's the compliance of this structure. So we have to think about what is delta, what is P, and how do we get that from an elastic analysis of this structure. So think about this, right? This is delta over 2. You think about beam theory and cantilever beam, right? This is exactly a cantilever beam under a tip load, right? So let's cut this guy out and make the assumption that this is a fixed cantilever. So this is what it looks like, right? So if we blow up this part, so this is why we call it double cantilever. The two sides is double. Now, how do we find out what the delta is? Right, P is here. P is being applied. So we know what P is. We just need to know the delta corresponding to this P. And that's easy from beam theory because delta is the amount of end deflection. Actually, delta over 2 is the amount of end deflection at the tip corresponding to an end node. This is something you get from solid mechanics. And if you remember, or if you don't remember, you can check just a classical result. From beam theory, the delta is PL cubed, L being the length of the beam. So this is length of the beam. E and I being the second moment of area, which is for, let's say that this is a rectangular beam, the second moment of area is BH cubed over 12, whereas the H is the height and B is the width, right? So into the page, that is the width, that is B, and here is H. So just collecting all this, I know the delta is this guy. I just calculate what C is. C is delta over P. And if I just do P, now L is the length of the beam, and that is the crack length, A, right? Exactly the crack length A. So it's just A cubed here. 3EI, that's delta. Oh, sorry. Delta over 2, because there's only half of it, right? Delta over 2, right here, right? Not delta. Delta is we define it to be the double, right? The whole thing. And therefore, we have delta to be 2PL, 2PA cubed, 3 over EI, and that has to be divided by P. So in the end, we get 2A cubed, 3EI. So then we can now apply directly the G formula, which is just P squared, 2B, B being the width, again the width of the solid, we assume to be constant at the moment, for the time being, and we have DCDA, P squared 2B, and then just differentiating that is very simple. So we get to a end result of B EI. Sorry. Right. So for this cantilever beam configuration, the energy release rate is this. Yes? So, I mean, again, you see that, we have to apply some linear elastic analysis where we calculate the energy release rate, obviously, because, we need to calculate the energy, which, first of all, we need to know the stress field or the deformation field. And in this case, we can use a simple beam theory. Sometimes you need to use, in most general situations, you need to solve a complex problem, complex geometry. We use finite element analysis, okay? And then calculate G. Now, some finite element analysis directly calculate this guy for you. Okay, so we're going to use Abacus. Abacus does that. He calculates. You have to define where your crack is. You can have a very complex structure. Then you define your crack. Then it tells you calculate this exactly for you based on the stress field computed. Now, this sort of analytical solution can be solved for some simple problems, right? So analytically, we derive this simple result for certain amount of geometries. I'll show you more what we can compute and what people use simple configurations for experiment, because we don't want to always go to finite element analysis to calculate this guy just to measure the fracture energy, right? So we come up with various sort of configurations, so that which we know the analytical solutions to, that allows us to calculate this. Now, so we're going to talk more about this next lecture, because that has also some very nice, very insightful observations we can make from this guy. So we'll see you on Thursday.